round robin CPU scheduling algorithm. So round robin is a preemptive scheduling algorithm. So in this algorithm, each process will get a small unit of a CPU time, and this is called as the time quantum. Okay, so after this time has elapsed, meaning that after the time quantum has finished, the process is preempted and added to the end of the ready queue. Then it will go back into the ready queue. So in this round robin algorithm, timer will interrupt after every quantum to schedule a next process. So meaning that after each quantum, there will be an interrupt. Okay, in terms of performance, a very large time quantum will lead into a first come first serve. It will be similar to first come first serve algorithm or the first in first out algorithm. Okay, if the quantum is too small, then it will lead to increased number of context switches, and we know that context switch is an overhead. Okay, so this is an example of the round robin, and time quantum given here is 4. Normally it will give the whole number so that it will be easier to calculate. This is just to simulate how the round robin works. Okay, so normally when given this time, this kind of algorithm, I would like to draw what is in the ready queue. Okay, so in this example, all processes arrive at the same time. So we have P1, and then we have P2, we have P3. Okay, so as usual, the round robin, the Gantt chart, it will begin at time 0. So at time 0, P1 will be executed, but at time 4, you can see that this is when the quantum ends. Okay, the time quantum ends, so P1 will be interrupted and then preempted and moved back into the ready queue at time 4. So this is at time 4. So now, because it has been in execution for 4 burst time, so instead of 24, now it becomes 20. Okay, so next process in execution will be the next process in the ready queue, which is P2. So P2 requires only 3, so we just add up 3 to it, meaning that until it completes its execution. So it finishes at 7. So once it's finished its execution, the next one will be P3. So P3 also requires 3, so plus 3 to it. Okay, so it finishes at 10. Okay, so P3 completes. Okay, now only P1 left in the ready queue. So P1 needs 20. Okay, so P1 will be executing until its quantum is finished. So by right, after the quantum finish, P1 will be interrupted, preempted, and moved back into the ready queue because there is no other processes there. So therefore, P1 is continued, will be continued doing. Okay, so but at every quantum, you can see that P1 is being interrupted until it finishes at 30. Okay, so this is the Gantt chart for the round robin. So to calculate the waiting time, so we have P1. If you look at here, P1, as though P1 begins at 10. So this is the waiting time of P1 actually. So it's 10 minus 4 because it has been in execution for 4 burst time earlier. So its waiting time is actually 6. P2 waits only 4 burst time, and P3, sorry, not burst time, waiting time, and P3 is 7. Okay, so this is the waiting time. Okay, so this is again the same example for the round robin. So it tells here that round robin, it gives a higher average turnaround time than the shortest job first, but it gives a better response time. Okay, so meaning that P1 is responded immediately. P2, it does not need to wait until P1 completes, but being responded after the quantum time. So meaning that the response time is better. However, the quantum time cannot be too large compared to the context switches. So the quantum time is usually around 10 milliseconds to 100 millisecond, and the context switch is normally is 10 microsecond. Okay, so if you look at here, if we have too large of the quantum time, we have very few context switch, but this does not mean that it will be good. Okay, because if the quantum time is too large, then it will be similar to SJF or the first come first served, right? But if the quantum time is too small, it will increase the number of context switches, and we know context switches is an overhead. So there should be a balance between the quantum time and context switch. Okay, so now we look at another example, and in this example, the arrival time is different. Okay, so we have a vary arrival time. So again, so we draw out the ready queue here. So at time 0, we only have P1 with the burst time of 24. Okay, so there is no other processor, so we begin our Gantt chart with P1 at time 0. Okay, so assuming the quantum time is also 4, so P1 will be executed until the quantum time finishes at 4, and at 4, P1 will go back into the ready queue, and this time the burst time is only 24. Okay, so there is no other process in the ready queue, so P1 will continue its execution for another quantum time, that is 8. Okay, so while P1 in the execution, we have P2 arrive at time 5. So P2 will go into the ready queue at time 5. So P2, and it requires 5. Okay, when P1 finishes its quantum time at 8, okay, so it finishes its quantum time at 8, so it will go to the ready queue, and it will be in sequence after P2. So it will be P1 here. Now the balance is 16. Okay, so the next process to be executed is P2. P2 requires 5, so until it finishes its quantum time at 12. Okay, so while P2 is in execution, so we have P9, and we have P3 here, arrives at time 9, P3, and it requires 3. Okay, and P2 only finishes at 12. So P2 here finishes at 12, so the balance is only 1. Okay, so the next process in execution once P2 completes would be P1, because P1 is the next one in the queue. Okay, P1 requires 16, so we give it until it completes its quantum time, plus 4, so 16. Okay, so meaning that at time 16, P1 will go back into the ready queue with the balance of 12. Okay, so next process will be P3. So P3 requires 3, so we give 3 until 19, and P3 completes its execution and will not go back into the ready queue. The next process will be P2. So P2 requires only 1, P2 requires only 1, so until 20, and it finishes its execution. So the next one will be P1. Okay, P1 requires 12, so we do it until it finishes its quantum time until 24. Okay, so 24, so we have P1, so the balance is 8, and then P1 again until 28. Okay, so meaning that at 28, so we have P1 again, the balance is 4. And finally, we have P1 again until it finishes execution at 32. Okay, so this is the Gantt chart for the round robin algorithm with different arrival time for the processes. Okay, so now we calculate the waiting time. For P1, if you see here, P1 waited for several times. So we have P1 waiting here, and then we can see that we have P1 waiting here as well. Okay, so now we have P1, this is 4, so 4 plus, okay, so P1 here, this is 3, and this is 1, 3 plus 1, okay, this is 3, this is 1, so 3 plus 1. And then we have P2, okay, P2 the waiting time, okay, so P2 the waiting time, because P2 only arrives at 5, so even if you see here P2 begins at 8, so it will be 8 minus 5, okay, P2 here, and then we can see that P2 waits again at this interval. Okay, so we have P2, so this is 4 and 3, so it will be 7. Okay, 4 plus 3 here, so it will be 7. And P3, okay, P3 begins the execution at 16, but it arrives at 9. So this is 10, 8. So this is the waiting time for P1, P2, and P3.